Hello, and today I'm going to present to you Lab 5, the Falling Slinky from Physics 2211. The main purpose of the lab was to model the motion of a slinky dropped from rest from a certain height and analyze how different forces acted on the slinky, having the slinky as the system and the earth and everything else as the surroundings. The main physics principles present in the lab are Newton's second law, gravitational force, drag force, and tension force. The results showed that when all of the forces acting on the slinky were taken into consideration, then the computational model was very accurate with the experimental model. Here are the formulas used in the lab. The position and velocity update formulas were used in order to update the position throughout each iteration. The formulas for the gravitational and tension force are equal but opposite to each other in sign. And we also need the drag force, since the forces acting on the slinky are the gravitational, tension, and drag force. The initial position and velocity of the slinky were obtained through tracker, and the average mass of the slinky was seen to be 0.22 kilograms, and the time span in which the data was recorded was 8.667 seconds. This is a video of my tracker analysis. As you can see, the origin was said to be the end of the spring, since the goal of the lab was to analyze the bottom of the slinky while stretched and being dropped from rest. You can see that when the slinky is released at first, there seems to be no motion on the bottom of the slinky. However, later on, we see that when the top end of the slinky reaches the bottom end of the slinky, the bottom then starts to move. When the top of the slinky is falling towards the bottom of the end of the slinky, the force of gravity and the tension force are equal in magnitude, but opposite in direction. This means that these forces can cancel each other out and there is no force acting on the bottom of the slinky. When the top end reaches the bottom end of the slinky, the forces that are now acting on the bottom part are the drag force and the force of gravity, which do not cancel each other out, and causes the bottom of the slinky to start moving towards the ground in constant acceleration. This is my computational model, which was based on the code from Lab 2, Motion of a Falling Object. The initial conditions had to be updated, such as the mass, initial position, and velocity of the slinky. The constant b was determined through trial and error. For the first while loop, the time was set to be less than 5.583 because during this time interval, the only forces acting on the bottom of the slinky were the gravitational and tension force, which canceled each other out. The position and velocity update formulas were placed into the code in order to update the position of the bottom of the slinky. For the second while loop, the time intervals were between 5.583 and the final time, since during this time the forces acting on the slinky were the gravitational and drag force. Finally, the position and velocity update formulas were also placed into the code. Here you can see that for the first while loop we only have the force of gravity and the tension force acting on the system, and we calculate the Fnet by adding these two forces. And then for the second part of the while loop we have the drag force and the force of gravity acting on the system, so the Fnet will be just the addition of these two forces. These images show the results of the experimental model obtained from tracker and the computational model. As you can see, the graphs are similar to one another. There are some sources of error that could be caused due to the measurements taken from tracker, since the video was somewhat blurry. But overall, the graphs have the same shape, indicating that the forces that acting on the slinky were accurate as the ones determined in the computational model. The bottom of the slinky did stay stationary up until the top end of the slinky reached the bottom end of the slinky. Here, for the constant horizontal line in both of the graphs is when only the gravitational and the tension force were taken into account, and the forces cancel each other out, which meant that there was no movement at the bottom of the slinky. Here in this part, we can see in the computational model a straight line indicating that there were no sources of error. However, for both of these sloped lines, the drag force and the force of gravity were taken into account. That's why we see a constant acceleration in the bottom of the slinky. And here we see the sources of error, which could have caused due to tracker or other forces that may have not been taken into consideration in our computational model acted on the system.